Hello, my name is Yiltan, and welcome to my presentation, Micro-Benchmarking and MPI Partition Point-to-Point Communication. So the outline of this presentation, the introduction, where I explain existing multi-thread point-to-point communication, and then MPI Partitioned. Then I'll explain the motivation behind this work, and then the micro-benchmark and the results. I'm going to explain them side by side, so it's easier to follow. And then I'm going to explain then our conclusion and our future work. So HPC is often used to solve large complex problems, and communication is one of those problems. The message passing interface is one of the most popular programming models, and it provides multiple communication APIs, point-to-point, partitioned, and RMA, and collectives. And regardless of which model you use, you have the four main modes: single, funneled, serialized, and multiple. So I'm going to start explaining some of these modes. So MPI threads serialized. So we have a code block on the right. All work is executed in this parallel region. We wait for the threads to join, and then the data is transferred. So some threads may finish early, some may wait late, and they just become idle, and they don't do any work, and they don't communicate, which is non-ideal. Another issue is network bandwidth becomes underutilized because there is that period where they could have sent data, but they do not. Then we have MPI thread multiple. So we have the code block on the right again, and each thread does some work. And then once it's ready, MPI send I receive is called, and then finally we wait for it. So this looks great. Communication and computation with multiple threads. So, but there are some problems because sometimes this is serialized, and this is due to limitations in the hardware or some locks that may occur. Multi-threaded communication usually has issues with MPI's messaging queues. So again, these are locks that need to be locked and unlocked to put the messages on the queue or read from the queue. So MPI partitioned. The goal of MPI partitioned is to alleviate some of those issues. So we have MPI P send and P receive in it. And these are used to initialize the communication between the two processes that will be communicating. So here message matching occurs. And as this is done preemptively, no wildcards are accepted. So in the code, this is done in the serial region. So we don't have the same issues with access and lock as we did with the other model. Then we call MPI start. As it may indicate, we start communicating. So we launch the parallel loop as before. We do our work, and once the data is ready, we call MPI P ready. So this just marks that partition of data as ready to transfer. It doesn't necessarily transfer the data. And then P arrived. It just checks if the data has arrived. And this is optional, and some optimizations could use this. Then MPI wait all is used to mark that all the communication has occurred and we are finished. So a good implementation does not have the serialization issues of MPI point-to-point. So it's the P send and P receive in it, alleviates some of the issues with the message matching queue, and then here we just mark the data as ready and we don't actually transfer the data, and that's done by the implementation. So there's some good techniques that can be used to avoid the limitations of MPI thread multiple. So a diagram that could be easier to understand. So here we communicate, exchange the relevant information, partition, count, message, size, etc. Message matching also occurs, and then MPI start is called, and then the threads spawn on both sides. Once the data is ready, we transfer it, and then we call our MPI wait. So the motivation for this work. So commonly used benchmarks don't support MPI partition. So it was only added in MPI 4.0, so it's still relatively new. And SMB, OSU, and IMB do not support it. Traditional point-to-point benchmarking techniques do not work for MPI partition. And this is because we could use the same metrics, latency, bandwidth, but we'd get the same results because those are measuring the actual hardware capabilities. Whereas with partitioned, it gives us some features that allows us to transfer data early and be tolerant of noise on the system. So this is something that we may not be able to see with those metrics. So no production application uses MPI partitioned. Again, this is due to how new it is. So we ask ourselves, can we discover possible candidates? So our research questions, can we design an MPI partition micro benchmark to address the following? How can we understand the behavior and performance of MPI partition? So to propose optimizations in the future, we need to understand how does it work at the hardware level. And we also need a reference point. So if we make an optimization, we want to say this is what we had before and then what we gain. And then how could existing applications benefit from this programming model? So as I said, we want to see possible porting candidates, but what can we do to work this out? Then finally, what are appropriate partition sizes for application developers to use? So if someone's building a new application, they could naively pick certain partition count, but it may not use MPI partition to its best capabilities. So our micro benchmark design. First, we start off with MPI point-to-point, and this allows us to look at the partition communication and isolation between two processes. So we have overhead, perceived bandwidth, and early bird communication and availability. I'll explain them in more detail in a few slides. Then communication pattern. So the commonly used Halo 3D and Sweep 3D. So this allows us to look at MPI partition when there's multiple processes involved. How could it work then? And then with those metrics and communication patterns, micro benchmark allows us to use different noise models. So single thread delay, which is when one thread is delayed and then the others continue their computation. And this happens, let's say there's a CPU context switch or something like that. And then uniform and Gaussian probability distributions, and we sample a number and we apply a delay to each thread. So this allows us to look at what if there was some imbalances in the noise. And there's been papers to show that system noise can model a Gaussian distribution. So that is partially why we chose that distribution. Then hot versus cold cache. So a lot of benchmarks use a hot cache, and that gives us like a upper bound of like what performance we could expect. But a cold cache allows us to look at what is the more realistic thing that we could see within our application. So before I explain the metrics, I'm going to explain the experiments because I'm going to show you the results and what we're measuring in parallel. So we use the Niagara supercomputer at Skynet, which is a 20-core Skylake CPU. We have an EDR network, and we use CentOS and MPI and UCX. And then for MPI partitioned, we use MPI Pickle because at the time of writing this paper, MPI partitioned implementations were not mature enough. So this library, which is the partition communication library, has been used by other preliminary works on partition communication to evaluate it. So what is the cost of using MPI partition? So we want to know this because if we're going to write our application using it, we want to see what can we gain, what can we lose? So we have the metric on our right-hand side, and we have T part and T point-to-point. So for T part, we measure each partitioned data transfer, and then we compare it to point-to-point. So if we look at the diagram, T point-to-point is pretty straightforward. T part, so I'm going to explain what I actually do. This is a rough estimation. So each partition is measured, and then we have the start and end time of each partition data transfer. And then anytime those communications overlap, we remove one of the overlaps. So if we look at thread 3 and thread 4, these two overlap, so I would remove one of the overlaps. So we would find the continuous time from here to here. So in this diagram, T part is exactly what you see, but there may be scenarios where there's more gaps between communication, and that is the general algorithm we use to calculate T part. So our overhead results. So here are results for partition point to point for 10 milliseconds of compute. So partition count correlates with overhead, and overheads mostly impact small messages. So let's dig into this. So the reason we see more overhead with more partition counts, and especially small messages, is because let's say you have a buffer of, let's use 1K, and you split it into 2 partitions, then you have 2 512 buffers. And as the partition count increases, you are further subdividing that buffer. So if once you to send the data across the network, there's going to be some overhead of adding headers or other information in the transfer. So these small overheads tend to impact the smaller messages, which rather than the large messages, which are bandwidth limited. So perceived bandwidth. This metric we didn't propose. It was in prior work, but we included it for completeness. So we asked what would be the required network bandwidth for MPI point-to-point to perform the same as MPI partition. So if we have a MPI partition send timeline, T part last would be the time to send the last data transfer. So when we look at this equation, this just looks like a regular bandwidth. Just the time measurement is something slightly different. So all of this data is sent early, and this thread, this communication occurs last. So this is the equivalent network bandwidth we would need from a point-to-point to behave the same, because from the perspective of the application, this is the communication time. So our benchmark allows us to look at different noise. So we have 10 and 100 milliseconds, different compute. So we have 10 and 100 milliseconds compute and different noises from 0 to 10. And again, with different partition counts to see how that impacts things. So with 0% noise, we see something similar to our traditional bandwidth curve. For larger partitions, we see some noise, but that's just from waiting for 32 threads to align in our measurements. And then peak bandwidth is obtained for large messages, regardless of the noise compute. So these medium messages, sorry. And then for large messages, it drops back down. So we see it here, it drops back down. And that's because network bandwidth is our limiting factor. So why do we see these peaks? It's because some of the data can be sent early before the thread join, and it allows from the network to be the communication to be spread over a longer period of time rather than bursts. So application availability. So if we switch to MPI partition, how much extra work could the application do? So there is an equation in the paper, but this diagram is pretty straightforward. We have all this extra time that we could do something right here. And that could be compute, communicate, but anything. So how much do we gain from switching to this model? So this is our application availability with 100 millisecond compute, 4% noise. So on the left-hand side, we vary the partition counts. And on the right-hand side, we vary the noise distributions that we have. So increasing the partitions improves the application availability. So when we look at 2 partitions here, we do gain something, but the larger partitions is this a lot more, because for a large partition, let's say 32, with a single thread model, send model, all 32 threads would be delayed. Whereas with partitioned, 32 of them could continue, 31 of them would continue, and that last one would catch up. So it allows us to do more work in that period of time by freeing up those threads and not waiting. So depending on the type of noise the application has, we have different availabilities. So single thread delay impacts smaller messages a lot more so, because those single messages have a fairly low latency and they have to wait a relatively large amount in comparison to the noise. And then for these two distributions, we hit our peak around here where they all hit roughly the same spot. So depending on what you see in your application, could give some insight into what message size could be appropriate. And yeah, less beneficial for very large messages. So same reason with our peak bandwidth, T bandwidth metric previously, the network is the limiting factor in our results. So early bird communication. So how much communication occurs before the thread join? How much communication do we overlap? So we have this equation, T before join and T part. So previous metric, we were looking how much do we free up? And then here we're looking how much do we send before our computation is finished? So that's what we're trying to quantify here. So we have the early bird communication with 4 and 10% noise at 10 milliseconds of compute. So more partitions, better overlap generally. And if you have more partitions, more threads have their imbalances and delays, and the more data we can send earlier, the better. And large messages, we generally get poor overlap. Again, this is just, we reach the limitation of the network hardware. So now we move on to the communication pattern sections of our presentation. So first we looked at Sweep 3D. And Sweep 3D has a lot of dependencies in its pattern, where it has to wait for other processes to receive the data before it sends it across. And generally, multi-threading performs better than single-threaded. So both of these, the green and the red, are better than the blue. And the MPI partition implementation we used was built on top of sentinel sieves. So we see not too much difference for these smaller message sizes. But we do see it for the large message sizes. So we think this is because our implementation uses persistent communication rather than a regular point-to-point. And that's where we see the difference. With highly optimized partitioned communication, we think we would see an even better result. So Halo 3D communication. So this is our figures for 10 milliseconds compute and 4% noise. So Halo Exchange, there's lots of synchronization. You compute, you transfer the data, and then you compute again. So we don't see too much of a difference with this. So this could be the communication pattern itself, or this could be further studied and look at other ways that you can implement this, because this is just one implementation of this communication pattern. But what we did notice is you can increase the workload. So in this figure here by 64x, and we only see roughly a 17% decrease in our throughput. So we can increase the work, but it doesn't really degrade the performance to an amount that is concerning. There is a trade-off, but that trade-off could be useful in certain scenarios. And we think it could benefit from work stealing schemes. So porting applications. So Sweep 3D communication pattern we showed had the most potential. And then Snap C, which is a C port of Snap, uses that 3D communication pattern. So we profiled the application, measured its communication, and we projected its speed up using our the performance we saw for those large messages in the Sweep 3D. So we do expect to see something if this application is ported. So let's conclude our work. We provide the first MPI partition micro benchmark sweeps. We analyze partitions with a range of different metrics. So metrics we saw, and then we also looked into partition count, noise distributions, and different ways of using the cache. So this allows us to look at those metrics from different perspectives. We also showed what communications patterns could benefit from partition. So at this stage, Sweep 3D could definitely benefit. And then Halo Exchange could benefit in some scenarios, and that needs to be investigated further. So for our future work, we want to compare across different MPI implementations. So there is a limitation of what we did, but it was because at the time, MPI partitioned libraries were not mature enough. And then porting applications to MPI partition. So the projection we made, we want to realize that projection and see what we could get. And then we want to look at like accelerator triggered MPI partition communication. How can GPU kernels or an FPGA kernel trigger the work, the psend or parrive? And then MPI partition collectives. Collectives is the natural extension of point-to-point. So we'd like to acknowledge SciNet and Circ in the Digital Research Alliance of Canada, and thank you for watching our presentation.